Hello students and welcome back to my YouTube channel. Today we're going to introduce an idea from this number theory unit called Euclid's Lemma. Now Euclid's Lemma, as you see right here, it says for all x's and y, and sorry about this e here, this is as good as I could do in terms of trying to get that curvy little e typed. But anyway, for all x's and y's that are elements of the set of natural numbers, if p is a prime such that p is a divisor of something that can be expressed as x times y as two more, natural numbers, of course, then that prime number divides either x, or it divides y, or it divides both. So, quite simply put, so if, for instance, I know that, obviously I know 2, for instance, divides 106, right? So, that means that 106, of course, I could just say, hey, look, that's 2 times 53. Fine. Then 2 is the divisor of 2, or 2 divides 53. One or the other. Obviously not the 2 divides 53, but we know it definitely divides 2. Anyway, but you can do this literally with any natural numbers that fit this situation where p is a prime and x times y represents some other natural number that p is a divisor of. Now, this work leads to an important discovery here. When checking factorability of a number, one needs only check the divisibility of prime numbers less than the square root of that number. Now, we don't really need to find the actual square root of the number in question. It's sufficient to simply find the next larger square number. So, give this example here. Check to see if 201 is a composite number. So, in this case, the next larger square number is 225, because 225 is 15 times 15. So we really only need to look at the set of primes less than 15. So let's write those out here. So there they are, 2, 3, 5, 7, 11, and 13. If 201 fails to divide by any of those, it has to be a prime number. Obviously, since 201 is not even, we can strike, strike 2 from the list. So obviously won't divide by 2, but the search is over on the next one. It definitely will divide by 3. And again, I don't even have to actually write out the division. When I see 2 plus 0 plus 1, 201, right? Just add the digits, and I'm going to prove that soon. It will divide by 3. 2 plus 0 plus 1 divides by 3. Therefore, the whole number itself divides by 3. So, in this case, 201, we know, is composite. Relatively simple. All right, what about 457? Is this a prime number? Well, we're going to start by considering the square of each prime number until such a square exceeds 457. Now, in this case, the largest prime we're going to test is 19, because 23 is the next prime number, and when I square that, I get 529. That's too big. So let's just consider the set of numbers 2, 3, 5, 7, 11, 13, 17, 19. So, I think it's pretty clear that, looking at 457 here, it's pretty clear that it's not going to divide by 2. It's not an even number. 4 plus 5 plus 7 makes 16. Wait a minute, that's not going to divide. So I know it's not going to divide by 3. It doesn't end in a 5 or 0, so it's not going to divide by 5. Now this, let's see, 457. Maybe it divides by that. Let's try it out. So I take 457. I do just good old-fashioned long division here. 7 into 45 6 times, like so. 45 minus 42 is a 3. 7 into 37 5 times. Oh, there's a remainder of 2. So, no, it's not going to be divisible. All right, by 7 anyway. So I should line that out. 457, does it divide by 11? Well, I know that goes in 4 times. And 17, oh golly, that goes in once, so the remainder is 6, so that's not going to work. How about 13? Maybe 13. Maybe we'll get lucky here. Let's try that out. So 13 into 457. And 3 times 13 is 39. It's going to be 67. This goes in, let's see, 13, 4 is 52, 5 is 65. Wait, so 65 I should say. But either way, it's pretty clear it's not going to work. So that's got a remainder. That's not going to work. All right, fine. Let's move on to 17 then. Getting close to the end, right? So better do by one of these, or if it doesn't, that means we have a prime. 3 times 17 is 51. It's too big. Let's try it by 2 then. It's going to be, oops, I accidentally held it down there. That's okay. That's going to be 117. 17, oh boy, into this. I know 6 times 17 is 102. 7 times 17 is going to be, let's say, 9 up 119. It's going to be too big. I can see that that's not going to work. And last one, it's either divisible by 19 or I know it's got to be a prime. That goes in twice, 38, 7. Does 19 go into 77? So close. 19 times 4 is 76, but close isn't good enough, folks. We have a remainder of 1. So, therefore, we know that it is a prime number. Prime. Actually, you know what? Let's say, I'm trying to change my mind on how I'm writing this. I'm going to say we know that 450, I'll just say so, 457 is prime. How's that? And we'll just leave it at that. So, the other thing I want to talk about here is some algebraic evidence. I've talked about this before, how numbers, okay, when you square some number that ends in a 5, there is a certain pattern to it that allows you to do the mental math like super duper fast. So when I do x plus 5 here, folks, algebraic multiplication here demands that when I'm multiplying these, I really distribute both. I say x times x and the x times the 5, like so. And I'll write those out. X times x means x squared, and then the x times 5 is positive 5x. Now I'll do it with positive 5 times x, and the positive 5 times positive 5 gives me another 5x, and I write 25. Now, when I have this here, I know, I know I can add these two together. These, boys and girls, these are considered like terms. I'm going to expect you to know what that means next year. I can simplify those two like terms into 10x. See? Understand this here? Yeah. That became 10x. Now, with this, I want you to consider that I could group this up like so. And now I can factor out x, because x squared plus 10x, they both divide by x. So I'm going to rewrite this as x times, now I'll write x plus 10, leave that behind. The plus 25, nothing happened to it, did it? So what I have right now is I've got what amounts to be, two different factors, x times x plus 10 with 25 added on to it. The reason I'm showing you this is because when I have some number that I'm squaring that ends in a 5, say 45 squared, the implication here is that this tens place right here is represented by that x. That is to say, I can write this as 40, because the x is it's representing 4 tens here, so 40 times 10 more than 40 is 50. That's pretty easy to mentally add in your head, right? 40 times 50 is a 20 with 2 zeros. And then there's 25 added on. That's right, 2025. Pretty easy to do mentally, isn't it? I can do it again. I'll do it with 75 squared. 75 squared is going to be 70 times 80. The x and the x plus 10. And then I'll add on 25. 70 times 80 is, 7 times 8 is 56, so it's a 56 with 2 zeros. Add 25 to that. That's easy to do mentally. 5,625. Ain't that a cool trick? Complete through exercise 45 today, please, on page 49, if you will. And have a great weekend. Smash that like button and subscribe to my channel and be good for your parents. Bye-bye, everybody.